In this video, I'm going to show you how to customize a YEP. So if you go to I'm running on the main Instant NFT website right now, but the contracts are pointing to the final version of everything that's running on Rinkeby. So, and I have, if you have any YEPs in your wallet that you're connected to, these images will get replaced. I own one YEP. It's this first one right here. So if I scroll down, I can see I have my YEP here, and the editor's empty, which just means that I haven't done any customization for this YEP, and it's just doing using the base scripts right now. The customizations that we allow it's open-ended. You can do really whatever you want, whatever Gyve and Fyrd allow, which is anything. But we recommend that you start with our base scripts and try to probably keep the YEP looking like a YEP. It has kind of an iconic look, but you're not required to do that. So if I scroll, we have a little debug environment here. If I scroll down, and I can load the base scripts by clicking this button, and you'll see that this is the base scripts for the Gyve, and it contains Fyrd code also that generates YEPs. So it's a good example of first of all, YEPs are on chain. They're 100% on chain, and so this is a good example of how to make an on chain NFT, and that's what this tutorial will be about. And we use a lot of the capability of Gyve and Fyrd to generate this. The Fyrd is used for the floating point calculations, and it's an array processing language. I'll go into some detail about that. But that's what generates the hair, and the rest of it is, most of this is Gyve code. So I'm gonna keep these videos to 15 minutes max. So this one I'm sure will run over into at least one more video. I'm gonna go into a fair amount of detail about how Gyve works, and a lot of detail about each individual statement and all the primitives and methods. So yeah, if I repeat myself or I'm repetitive, just bear with me, but I want to give you as much information as you can so that you can understand what's happening. So our test environment, there's and we have an online editor here, and there's also a little debug window here, and the main thing that you'll be doing a lot is modifying code up here and then testing it. So I'll just push the test button now to show you how that works. Yeah, the test button, it uses the debug token URI function that we have internally. Everything is still executed on chain, except that it passes in the scripts that are here instead of the ones that are inside the contract. So so if whenever you click the test button, it'll generate it sends a different seed each time, so you can get a pretty good idea of the variation that you're going to get in your algorithms. So first I'll just talk about a little bit about the token URI function and what that's used for, and why that's required in an NFT. So that when you have a NFT running in a contract, somehow the metadata and the data for that NFT has to be acquired, and it's done through what's now a standard NFT method called token URI, and that's called, and it has to return a URI that can be used to retrieve the metadata and the data for this NFT. So in most cases, for example, if you were to look at the art blocks contract on Etherscan, and you were to go to you can go to the read contract, and you can you can look at the token URI function and actually execute it. So if you added a valid token ID, what it would return is just going to be a URI string to a server, an art block server. So whoever gets that that URI, OpenSea, or wherever it's getting displayed, that they use that URI to get the metadata for the NFT, and the metadata is in JSON format, and it's called the metadata standard. It was defined by OpenSea, mainly because they were the first ones to do it. So everybody has to abide by that standard. So like I said, most NFTs will just return a URI, but there's a better way to do it, and that is to return what's called a data URI, and it's a URL, but it also contains the data for the entire payload for that URL, so it doesn't have to call a secondary server. And that's what we do, and that's all done on chain. So when the token URI function gets called for one of our NFTs, Instant NFT, it's going to execute this Gyve script on chain, and that's what the Gyve script does. It's generating the metadata and the data for your NFT. So the NFT metadata, it's a standard, and it's JSON, and there's certain fields that you have to set in order to comply with the metadata standard. Like if you look here on lines 72 through 74, we're just setting some of the JSON fields, the external URL, the name, and the description. So yeah, the whole goal of the Gyve script is just to generate the metadata, and in this case, you can also have an on-chain NFT, which we're doing here, and it will generate the actual image data on chain also. So to do that, we wrote this on-chain programming language called Gyve, and it's a Lisp dialect. And I'm not sure if many of you have probably seen Lisp, but some of you may not have. It's maybe the oldest programming language. It's very old, but it's it's still used quite a bit today, and the main reason we chose Lisp is it's very simple to parse and execute. It has a very simple execution model, but it's also quite flexible and powerful. So Lisp, there's only one syntactic form in Lisp, and it's a parenthesized expression. So that's why you see a lot of parentheses in Lisp. But if you look inside any of the parentheses, there's just a number of terms, and the first term is a primitive or a function or a method, however you want to view it, and that's really what gets called when the expression inside the parentheses is executed, and the rest of the terms after that are just parameters to that primitive or method. So if you understand what the first term is in any of these parenthesized expressions, then you'll know what it's doing, and Lisp it's fairly, we use there's a lot of string data that gets generated from these on-chain NFTs, and Lisp it's fairly easy to look at and understand once you look at it for a little bit. So you can kind of see what's going on, just even if you don't understand Lisp, at least for a lot of things, especially when we're starting to generate the SVG data, down here in these lines. But yeah, once you get the hang of Lisp, I think you'll understand it and be able to write it fairly easily. So for Gyve, we just want to generate the JSON metadata and the data for the NFT. So we have a lot of primitives built in that are designed to do that. So I'll just hop into it, and I'll explain a few of the things that are happening here. So the $F function in line 1, that's defining an internal function. We can define our own internal functions. We provide a lot of primitives, but in many cases you'll probably want to define some functions to make whatever you're generating easier. So in this case, there's a lot of SVG things that we're doing here. Like the line 1 just generates a translate statement that's used inside SVG, and 2 is a rotate, 3's and a way to, it's an ellipse. There's ellipses in SVG. 4 is there's a color format called HSL, and that's what we use inside the YEPs. And that's what these all are. They're just generating something, either a string or an SVG statement. So the comma operator in line 1 right here, that's a concatenate, so that's just concatenating whatever follows into a string. And maybe meant to mention another one on line 3, if you just before right here on the ellipse, the less than slash, that's an XML primitive that we provide, and it generates it's going to generate an XML statement. The first parameter is the tag, and then there's a bunch of attribute value pairs that follow that, and then this will generate a valid XML statement. So this is it's a generative algorithm, and we want to generate different, hopefully a different variation every time it's executed. And so we have some random number generators that you can use to, inside your algorithm. So for instance, if you look at lines 11 through 17, this is where we're generating the colors that we're going to use for our palette. So line 11, it's picking a base color for this iteration, and it uses HSL, so the colors are 0 to 359, or 0 to 360. That's what colors you can pick. So there's 360 colors in HSL, and we're just picking this. Line 11 is saying pick a number between 0 and 360, and that's going to be our base color. And the S and the L are saturation and lighting, and we're just picking a random number in those ranges. And so we need other colors that make sense, based off of this base color. So line 14, it's calculating the complement color, which is if you add 180 to a base hue, that's the complement color, and it needs to be inside the range 0 to 360. So we use the mod operator here, the %, to make sure that it stays in that range after we do the addition. And then we're picking another color that's 90 off of the complement color, and it just makes sure that it's another distinct color. And I think one's used for the background and one's used for the eye color. And then we also, these are to generate the hair color. There's 2 hair colors. One is, it's always going to be a very light color, and then we have a highlight that we put in, a small number of the hairs just to make it look a little better. So I'm already up to about 14 minutes, so I think I'm gonna stop this video. It'll be called part 1, and I'm gonna continue this in part 2.